I'm Martin Livshits. I'm a principal engineer at Confluent working on core Kafka. And one of the things that I've done recently is KIP-939, which introduces two-phase commit and also describes how you could do atomic dual writes between Kafka and some other databases. And so the quick agenda for this talk, I'm just going to quickly do a recap for US in Kafka that exists right now. Then I'm going to describe two-phase commit and how it works. And then finally, I get into the details of the dual write recipe. And hopefully, we'll have some time for the questions at the end. And so let's look at Kafka exactly one semantics, right? So like when I talk about Kafka and me working on transactions in Kafka to my friends, they sometimes ask, like, Kafka is such a simple system, why do we need to have transactions? And here's a simple motivating example for a simple system. Let's say we want to copy messages between two topics, and maybe not just copy, maybe we do some simple thing like encrypt fields that contain sensitive information. But the very basic and fundamental flow is we just consume message from the source, we produce it to destination, and then we commit offset. And at the bottom, I sort of running an example where we start with one message that is consumed from the system and produced to another system. Then we move to message 2, and then we have this kind of two steps of producing and then marking it as consumed, and everything works well. But when we come to message 3, we produce it to the target system, but we fail before we can mark it as consumed. And so when we restart, we have to restart from message 2, and this results in a duplicate. Right? So like even with such a simple scenario, we actually have a problem in the system. And so we could try to do some simple fix, like we could reorder the steps, and then like would we fix this problem? We would fix that problem, but we create another problem, and basically with this situation, what we can get is to just have a data loss, and like so there is no simple fix for this problem. To fix this problem, Kafka introduced transactions, and now with these two steps, atomically they could be part of the transaction. And so like if you do these operations within the transaction boundary, then this operation will succeed or fail atomically, and you will never get into a situation when you have duplicate messages or data loss. And this is called exactly once. And so this is very old functionality we all know and love. It introduced in KIP-98 like 7 years ago, released in Kafka 0.11, and we made a bunch of improvements over time. We're still improving this. But there is one problem, is that it only works in the same Kafka cluster. And if you want Kafka to be a central nervous system and connect other systems together, it would be good if we could also have atomic operations that happen between Kafka and other systems. And so the technique to do this is also kind of old, well-known technique. It's called two-phase protocol. And we have a KIP in Kafka that accepted a couple months ago, so celebrate. So when this KIP gets implemented, Kafka will be able to participate in two-phase commit, which will ultimately allow Kafka to commit to have atomic writes between Kafka and other data sets. And so let's kind of dig into the two-phase commit protocol. So instead of, so it's like if applications wants to commit data to multiple participants, instead of committing individual transactions into each participant, which would have a problem of like non-atomic broken transactions, it would write data to the participants, but it would send a commit message to the transaction coordinator that would first run a prepare phase, and if prepare phase is successful, then it will write a commit decision and would communicate the commit decision to the participants. If anything is failed before the commit is successful, then the transaction is aborted, and then the abort decision is communicated. And so now let's kind of walk through example to illustrate how this protocol works. So assume that application wrote all the data to all the participants and is ready to commit. So it will issue a commit operation to the transaction coordinator, and then transaction coordinator would run the first phase of the two-phase commit, which is prepare. It will issue prepare operation to the participants, and once participants are prepared for this transaction to be committed or aborted, then they reply yes to the transaction coordinator, and then coordinator records a commit decision. This is the point where transaction is committed, and it's just a matter of time when it becomes communicated to the participants. And so this is like a success case. Obviously, if anything fails during this protocol, then the transaction will get aborted. And so now what does it take to implement a two-phase commit protocol? So it's basically all about prepare. So if a system has an operation that is called prepare, that has properties that the prepared transaction is ready to either commit or abort, then it's a system that supports two-phase commit protocol. And so prepare is a kind of special operation. It needs to make sure that whatever happens in the system after prepare cannot lead to a failure. So if the system has replication, all the data needs to replicate it, flash to durable storage, it cannot be aborted on timeout, it cannot be aborted on restart, failure, it cannot anything. And so this prepared transaction could be in doubt for indefinite amount of time until the decision is communicated to the participant. And so now if you look at Kafka, there are a couple things that would break this promise in the current system. So the first thing is that when you run init producer ID, when you start your transactional client, it will abort any transaction that is running on the system currently. And so obviously that would break the two-phase commit promise, and we need to introduce a new flag that for two-phase commit, the application could communicate to Kafka to say, okay, please keep any prepared transaction so that restart of the client wouldn't accidentally abort a two-phase commit transaction. So the second thing that prevents two-phase commit protocol from happening is that we have a limited timeout on Kafka transaction, and the broker would eventually abort a transaction if it's running for too long. So we obviously have to eliminate this feature for the two-phase commit transaction, and so that's a second change in Kafka that needs to be done. So eliminated timeout obviously leads to a fundamental problem that Kafka cannot self-recover from such a transaction, which is not a problem of Kafka implementation. It's just a fundamental problem of two-phase commit protocol that is present in any system that supports that. So to mitigate this problem, we also introduce a couple of changes. One is that we have a special ACL so that admins could only allow trusted application to run two-phase commit so that they can make sure that the application is available and clean up after themselves, and they could communicate to application owner if they need to resolve any in-doubt transactions. And then we also introduce a break glass functionality to force terminate in-doubt transactions if Kafka admin actually talked to application and figured out that the transaction needs to be aborted. And so this slide pretty much is what KIP-939 is in a nutshell. So now, two-phase commit protocol actually has a very interesting feature is you actually don't need to support two-phase commit in the last participant as long as the other participants support two-phase commit. And so the trick to do this is to use prepare phase on all the participants, and then for the last participant, you just could use a single transaction on the last participant to store data update and store transaction decision at the same time. And so it's still two-phase commit because you cannot run prepare and the last commit in parallel. So like there is a distinct prepare phase when the other participant kind of get the prepare, and then there is kind of prepare and commit phase for the database, and then there is like another commit phase to communicate the commit decision. But this trick actually eliminates the requirement on the last participant to have two-phase commit in order to actually implement the protocol. And so what it does for Kafka is it actually enables this dual write recipe when you could take any database that has transaction support, and you could use Kafka with two-phase commit protocol, and then you could use this trick to store the commit decision in the database, and you could achieve atomic writes. So this is kind of the main idea, and then let's kind of look into the dual write recipe itself. So the motivation is very similar to like exactly one semantics. You want to put data into two data sets, and like the simplest form of it, you probably want to make a change in the database, and then you want to log the state update to Kafka. And then like you could try to do it one order and say you try to put it in the database. Then if you fail to log the change to Kafka, then you basically get a missing log, and change in order obviously doesn't help. It helps to solve that problem, introduce another problem. So we don't really have a simple way to do it. Now, if we support two-phase commit protocol in Kafka, then we could do the sequence of steps to achieve the atomicity. So, and the sequence of steps would be you log the change to Kafka, and then you run prepare, but you don't commit, which is kind of what the two-phase commit protocol enables. Then we put data to database, and we store commit decision in the same transaction. And if we manage to successfully store data in the database, then we could commit Kafka transaction. But if we have any failures, we could restart, reread state from the database, and then we could know whether it was committed or aborted, and then do the corresponding operation in Kafka. So now, I mean, like, how do we actually store the commit decision? We cannot just store yes or no, because like we don't know whether the yes was for this transaction, for the next transaction. So we actually need to store it somehow to differentiate between the specific transaction that is prepared from some other transaction that was committed a long time ago. And as part of KIP-939, we introduce a new functionality. When KIP-939 is implemented, we're going to bump epoch on a transaction, and that effectively provides unique identity to every transaction in the system. And so this way, we basically can get the transaction identity from the prepare function. So the prepare transaction function actually returns a prepare transaction state that is kind of opaque state that can be serialized into a string. But under the covers, this state is just producer ID and epoch pair. And then the application would store this state in the database. And then we would compare this state to the actual prepared transaction. And if it matches, then we know that the transaction is committed. If it doesn't match, then transaction needs to be aborted. And so, like, let's kind of go through an example here. Suppose we have some application that logs the change into the changelog topic, and it modifies example data. Right? So example data is just some application-specific data that application needs to work on. And as part of the dual write recipe, it would also have a table with where it maps the transactional ID to the transaction state. And the transactional ID would be the configuration that you would get on your producer when you configure it. And so, like, so for every application, you would get like one record with the specific transactional ID, and then the data would be transactional state. And so now, suppose we get a new change that changes value from foo to bar. And so the first step of the dual write recipe is to log the change to Kafka, and then prepare Kafka transaction. So it's kind of grayed out here to show that it's still not like it's in doubt. So the Kafka transaction will in turn will return the new epoch, and we could see that it's like 43. So like the previous epoch was 42, and it returned 43. And then at the next step, we will basically save this data to the database as a single transaction. And so like in a single transaction, we will update the application state, which changes foo to bar. And in the same transaction, we will also update the transactional state to change the sort of epoch from 43 to 42. If the change was successful, then atomically we would get both the application change and the transactional state change, which effectively would record the decision. And so then when we complete the transaction in Kafka, we will pass the latest state from the database, which is the new state, and then Kafka would know that it is a commit, and the bar would get committed into Kafka, and now we achieved our atomicity, and the transaction is fully committed. So on the other hand, if for any reason the transaction fails and we read the data from Kafka and we see that this is like the data that doesn't match the currently running transaction, we will communicate it back to Kafka, and Kafka sees, okay, so this is the old transaction, and that lets it know that the change is actually aborted, and now we could abort the change, and we fully completed the atomic transition, which is like kind of abort the whole change in both data sets. Okay, so now I'm going to talk about like couple tricky issues. So like the example kind of goes through the basic stuff, but on restart, we need to make sure that we correctly load the data from the database. So for SQL database, it's somewhat easier. We could log the state by issuing select for update, where transactional ID means equals my transactional ID, and then all the steps would be executed under the log. So what effectively happens is that if there is any transaction that is pending from the previous incarnation, taking the log will make sure that we'll wait until the previous transaction completes. Okay, and then like doing this under the log would achieve the correctness. So for NoSQL databases, it's a little bit trickier. So most of the NoSQL databases actually do not support logs, and the way atomicity is achieved is generally by using version checks or conditions. So if an application wants to do an atomic read, modify, write operation, they would read data value, and when they read data value, they will get a version or condition. Then they could take the time to modify the value, and then they write the value back with the same version. And the atomicity is provided by the database when it checks the actual version, and then it would see if the version matches, right? So if the version doesn't match, then the operation fails, and the application would get an error that there is a version mismatch, and it will have to retry the operation with the correct data. And so here I get like kind of two concurrent writes going on. So they both write the same value, and one of the writers wants to change this value to ABC, the other one wants to change this value to XYZ. And then, obviously, to maintain atomicity, only one of them should be able to succeed. And so like in this case, the ABC guy got the first, and when they updated the data to ABC, they also bumped the version to 4, and then when the XYZ guy comes there, they see that the version doesn't match, and they will have to reread the record and retry the operation again. Okay, and so now when we look at the $write restart with the NoSQL DB, like a naive way to do it, we could just get the state from the record and then try to complete the transaction based on the state with the record. But there is a problem there. We actually don't know whether there is a transaction is still ongoing, and if it's still ongoing, it could actually complete and update the state after we already aborted the transaction and already kind of undone the part on the Kafka side. And this obviously breaks atomicity, because now we have a successful transaction on the database side that is not reflected in the in Kafka log. And so to fix this, we actually need kind of a little bit more sophisticated logic on restart. So when we read transactional state from the record, we cannot just use it on the database and then just like complete the transaction. We need to prevent concurrent transactions from completing and kind of messing the state. So to do that, what we need to do, we just need to update the transactional state with the same value to bump the version. So we don't want to change the value. All we want is to change the version so that basically, if the transaction comes and tries to update the data, it will not succeed because the version is updated, and it will bring the atomicity to the correct outcome so that we have matching Kafka log that matches the database state, which is kind of properly aborted state in both data sources. Okay, and so this is kind of the summary of the key ideas that sort of are foundation for the dual write recipe. So like the first idea is that last participant doesn't have to support two-phase commit, which opens the dual write recipe to all kinds of databases and like key value stores, all the kind of data stores that support transaction. All you need to support dual write recipe is just a transaction on the data store. So, and the second idea is that the commit decision is just derived from the Kafka transactional state, and the new KIP actually just provides a way to get this state, and so like as long as it's written into the database, that's all the application needs to do. And so like as part of the KIP, we also plan to add some code for examples with SQL databases and a few NoSQL databases so that people could actually look at what the correct code looks like and they could derive the application from there. Okay, and I guess this is it for the talk.